An autonomous vehicle must rapidly and accurately recognize objects that it encounters, from an idling delivery truck parked at the corner to a cyclist whizzing toward an approaching intersection. To do this, the vehicle might use a powerful computer vision model to categorize every pixel in a high-resolution image of this scene, so it doesn't lose sight of objects that might be obscured in a lower quality image. But this task, known as semantic segmentation, is complex and requires a huge amount of computation when the image has high resolution. Researchers from MIT, the MIT-IBM Watson AI Lab and elsewhere have developed a more efficient computer vision model that vastly reduces the computational complexity of this task. Their model can perform semantic segmentation accurately in real time on a device with limited hardware resources, such as the onboard computers that enable an autonomous vehicle to make split-second decisions. Recent state-of-the-art semantic segmentation models directly learn the interaction between each pair of pixels in an image, so their calculations grow quadratically as image resolution increases. Because of this, while these models are accurate, they are too slow to process high-resolution images in real time on an edge device like a sensor or mobile phone. The MIT researchers designed a new building block for semantic segmentation models that achieves the same abilities as these state-of-the-art models, but with only linear computational complexity and hardware-efficient operations. The result is a new model series for high-resolution computer vision that performs up to 9 times faster than prior models when deployed on a mobile device. Importantly, this new model series exhibited the same or better accuracy than these alternatives. Not only could this technique be used to help autonomous vehicles make decisions in real time, it could also improve the efficiency of other high-resolution computer vision tasks such as medical image segmentation. Categorizing every pixel in a high-resolution image that may have millions of pixels is a difficult task for a machine learning model. A powerful new type of model known as a vision transformer has recently been used effectively. Transformers were originally developed for natural language processing. In that context, they encode each word in a sentence as a token and then generate an attention map, which captures each token's relationships with all other tokens. This attention map helps the model understand context when it makes predictions. Using the same concept, a vision transformer chops an image into patches of pixels and encodes each small patch into a token before generating an attention map. In generating this attention map, the model uses a similarity function that directly learns the interaction between each pair of pixels. In this way, the model develops what is known as a global receptive field, which means it can access all the relevant parts of the image. Since a high-resolution image may contain millions of pixels chunked into thousands of patches, the attention map quickly becomes enormous. Because of this, the amount of computation grows quadratically as the resolution of the image increases. In their new model series called EfficientViT, the MIT researchers used a simpler mechanism to build the attention map, replacing the nonlinear similarity function with a linear similarity function. As such, they can rearrange the order of operations to reduce total calculations without changing functionality and losing the global receptive field. With their model, the amount of computation needed for a prediction grows linearly as the image resolution grows. But there is no free lunch. The linear attention only captures global context about the image, losing local information, which makes the accuracy worse. To compensate for that accuracy loss, the researchers included 2 extra components in their model, each of which adds only a small amount of computation. One of those elements helps the model capture local feature interactions, mitigating the linear function's weakness in local information extraction. The second, a model that enables multi-skill learning, helps the model recognize both large and small objects. They designed the EfficientViT with a hardware-friendly architecture, so it could be easier to run on different types of devices such as virtual reality headsets or the edge computers on autonomous vehicles. Their model could also be applied to other computer vision tasks like image classification. When they tested their model on datasets used for semantic segmentation, they found that it performed up to 9 times faster on a NVIDIA graphics processing unit GPU than other popular vision transformer models with the same or better accuracy. Building off these results, the researchers want to apply this technique to speed up generative machine learning models such as those used to generate new images. They also want to continue scaling up EfficientViT for other vision tasks.